Welcome to our new webinar series on extreme events and hazards. I'm Margaret Boone, Program Manager with the Southern Climate Impacts Planning Program, and I will be the moderator for today's webinar. Rachel Riley, SCIP Associate Program Manager, will be managing the webinar. This webinar is the second in a series of quarterly webinars that will focus on extreme climate and weather events and hazards that affect the southern United States. In July, we discussed hurricanes. The topic of today's webinar will be flash flooding. Today's webinar will feature a look at what causes flash flooding, along with a few examples from Jeff Becerra, Director of Research at the Oklahoma Climate Survey and Associate Professor of Meteorology at the University of Oklahoma, a discussion of National Weather Service River Forecast Center operations during flash floods, and a case study from Karen Crow, Louisiana, by Suzanne Van Kooten, hydrologist in charge at the Lower Mississippi River Forecast Center, along with her colleagues Scott Lincoln, hydrologist, and Jessica Smith, hydrometeorologist. And lastly, a look at the National Weather Service NEXRAD radar upgrades to dual polarization and what that means for precipitation and flash flooding real-time forecasts by Andy Wood, Instructional Support Meteorologist at the National Weather Service Warning Decision Training Branch. I'd like to briefly discuss the goals of this webinar series. We plan these in order to provide timely and relevant preparation and mitigation information to our local, state, and regional organizations, agencies, and business officials who are directly affected by these various extreme events and hazards. Each webinar will include preparation and planning information related to the hazard and products and information useful for monitoring the hazard. We want to assure you that the information is seasonally relevant. Since this is a quarterly webinar series, our next webinar will be sometime in early 2013. You may ask questions or make comments at any time through typing in your chat box. We will address questions at the end of the presentations, and we will also put up a list of resources that will be available. I'd like to turn it over now to Jeff Becerra.
Well, good morning or good afternoon, depending on where you're at and where you're tuning in with us. My name is Jeff Becerra. As Margaret mentioned, I'm the Director of Research here for the Oklahoma Climatological Survey. I'm also Associate Professor in the School of Meteorology here at the University of Oklahoma. One of my areas that I am interested in and currently am active in terms of research is actually flash flooding, and particularly flash flooding in urban areas. So that's what I'm going to kind of give an overview of today. Next slide. But actually, for a couple of quick questions that sort of need to be addressed, and since I'm leading it off, these are relevant questions, is what conditions typically lead to flash floods in the first place? Next slide. So if you go back, there's a great article published in 1979 by Bob Maddox and a couple of co-authors in the Bulletin of the American Meteorological Society, where they discuss the synoptic and mesoscale aspects of flash flood events. And their conclusions are really, there's 8 main conclusions that I wanted to point out that are important when looking at flash flood events. And these are, even though this was published over 30 years ago, these ingredients or conditions are still very relevant today. First of all, most flash floods were associated with convective storms. That seems to be entirely understandable. Heavy thunderstorms produce flash floods. It's not always the case. You can have orographic lift, for example, in the western parts of the U.S. With heavy rainfall rates in areas of extreme topography that are not convective. But in general, especially east of the Rocky Mountains and even over the Rocky Mountains from time to time, flash flood events are almost always associated with convective storms. Storms occurred when surface dew points were high, and that makes sense in the broader context that it has to be very humid. And we're going to talk a little bit more about that as we move on, but that was one of their initial findings. Relatively high moisture contents were present through a deep tropospheric layer. In this case, we're dealing with moisture in the atmospheric profile through the troposphere. In fact, the more saturated the atmosphere is through deeper depths of the atmosphere, if there's any type of lifting, that can release that into a high precipitation efficiency environment to produce very heavy rain. There needs to be weak to moderate vertical wind shear that was present through the cloud depth. So where the clouds and thunderstorms are existing, there actually needs to be weak shear, and that is important in the context that it allows the storms to remain quasi-stationary or at least redevelop over the same area. In a strongly sheared environment, that may not be the case. But in a weak to moderate shear environment, storms can remain over the same area, producing heavy precipitation. Another aspect is that some flash flooding events occurred when convective storms repeatedly moved over the same area. And sometimes you'll hear this referred to as training, or storms train over the same area. That can definitely produce flash flooding. A weak mid-tropospheric mesoscale trough help to focus the storms. So something in the mid-levels of the atmosphere has to be providing enhanced lifting, and a weak trough is often the focus for this weak lifting, at least weak to moderate lifting. The storms occurred near the mid-tropospheric large-scale ridge position, so downstream of the trough, near the ridge, and that is important because that it often allows for that weak vertical wind shear environment to exist. And that storms often occurred during the nighttime hours, so flash flooding events, while not always the case, many times were sort of a nocturnal type of event. Next slide. Now that was followed up in 1996 by another article that was published in Weather and Forecasting that I'd like to highlight, and that's by Chuck Doswell and a couple of other co-authors, Harold Brooks and Bob Maddox, and they were looking at flash flood forecasting, and they spelled out a couple of additional ingredients. And that for example, the heaviest precipitation occurs where the rainfall rate is the highest for the longest time. Now that is incredibly intuitive, but it's worth noting. You want to have, for flash flood events to occur, there needs to be a heavy rainfall rate for an extended period of time. And in this case, they were looking at, say, an inch, an hour type of rainfall rate or greater, or 25 millimeters an hour or greater. Would produce flash flooding in certain situations. That the precipitation efficiency is important. And precipitation efficiency is that ratio of the mass of water falling as precipitation to the influx of water vapor into the cloud. So there needs to be, if heavy rainfall is occurring, there needs to be a significant amount of inflow and more moisture being ingested by the storm to continue that high precipitation efficiency and high rainfall rate. Again, heavy rainfall rates are most often occur with deep convection, and the atmosphere must be unstable, and lift must occur from some other source to allow the air mass through the level of free convection and allow the thunderstorms to exist in the first place. And again, heavy precipitation must remain quasi-stationary. So these are, in order for flash flood events to happen, these are sort of the ingredients that need to be in place. And when there's an urban area, that can be a significant challenge. So let's go on to the next slide. And what I want to talk, you'll probably hear me talk a lot about today, is precipitable water. And it kind of takes into context a number of these moisture variables. But it's the total amount of water vapor within the column of the atmosphere. And most flash flood events yield very high precipitable water values. So the atmosphere has a significant amount of water vapor already in the column. That column is then lifted, the water vapor condenses, and precipitation occurs. So we're going to look at some precipitable water values, and so here, just wanted to give you a quick overview of precipitable water. All right, let's move on to the next slide and get on to a second question. So what role do urban areas play in flash floods, and sort of what are the impacts? Next slide. Well, the challenge of urban flash flooding, as opposed to, say, rural flash flooding, is that you have increased population and population density. There's a lot more people. The impacts are potentially greater simply because the flash flooding event is occurring in an urban area versus a rural area. It's sort of like the context of if a tree falls in a forest and nobody hears it, did it really fall? If a flash flood event occurs out in an entirely rural area where there's no population, it may not have much of an impact. That same flash flood event occurring in a populated area might have a devastating impact. And of course, these, flash flood events can affect urban areas worldwide. They're not limited to any particular location. Urban areas have a significant large zones of impermeable surfaces. So a lot of concrete in urban areas, a lot of asphalt. They enhance runoff. And instead of allowing moisture and rainfall to sort of penetrate the surface that just runs off, and that can enhance flash flooding. And often, many small watersheds may quickly reach capacity during a heavy rainfall event, and so flooding is exacerbated in and around these urban areas. And there have been some studies that increased aerosols may actually increase the precipitation and increase the precipitation efficiency. All right, next slide. So as populations grow, and worldwide we see that the populations are becoming more urbanized, the risk for urban flash floods are increasing. And they're often very difficult to forecast. Advisories, warnings of urban floods are often short-term products. And so, as I'll show you in an example here later, oftentimes the conditions favorable for flash flooding in an urban area, you may only have an hour or two, or maybe other types of, you may not have a very significant amount of time before an urban flash flood begins. I see a question from May. Are there risk maps of flash flooding in any urban area? To my knowledge, there are no specific risk maps specifically for flash flooding. There may be risk maps for flooding, but I don't know if there are any specific risk maps for flash flooding. At the same time, I think most urban areas, the local population knows those areas that may be most vulnerable. But I think in general that's sort of on an urban to urban area in a local population base, but I may be wrong. The increased runoff can quickly flood homes, businesses, and alter travel. So infrastructure, and often overall infrastructure will fail or may fail during a flash flood event, and that further threatens lives and property. All right, next slide. So I'm going to show you some cases of precipitable water. Now I'm going to take a second and explain this map. This is a composite analysis, annual climatology of precipitable water for the Washington, D.C. area. So the red line there, if you look on the x-axis, the bottom axis, that extends from January through December. So the months, you start off in the cold season, the middle of the graph has the warm season, and then it again tails off into the cold season. On the left is precipitable water in inches. So 0 on the very bottom, increasing to 2.5 inches on this particular graph. And as we begin in the cold seasons from January to February, if you look at the red line basically represents the mean, or the average precipitable water for that particular time of year at this particular location, in this case being the Washington, D.C. area. The precipitable water in the wintertime is relatively low, about 1/3 of an inch on average in the atmosphere. As the seasons warm, that precipitable water average value actually increases pretty significantly to almost 1.5 inches in July, and then it begins to tail off again into the fall and into the winter months. So the red line is important. That's the average value. Now what I've plotted are the precipitable water values from 4 different flash flood events that are on the bottom of the that are listed on the bottom of the slide. An event near Philadelphia, which is just upstream of Washington, D.C. on June 16th and 17th in 2001. A second Philadelphia flash flood event, June 12th and 13th of 2004. A Baltimore flash flood event from July 7, 2004. And then Hurricane Floyd in September of 2001. And all of those values are plotted there, and notice they're significantly above the average. In fact, they're above the 75th percentile, and they're actually very close or above the 99th percentile. And this, what this shows is that for all of these flash flood events, there was a significantly higher amount of moisture present in the atmosphere than what is normal on any particular time for that particular day, according to climatology. So when we look at flash flood events, I'm going to show you some more examples, and you'll see this trend repeat itself. That in order to have flash flood events, just in general, but also in these urban areas, you'll see these very high precipitable water content values, meaning that the atmosphere already has pre-existing conditions of increased moisture, and then something else comes along, lifts that moisture, and the precipitation efficiency tends to be real high. Now, I need to give credit. This was actually done. These graphs of annual climatology are actually NOAA products, and they were produced by the National Weather Service office in Rapid City, I believe, by Matt Bunkers. All right, let's go on to the next slide. So here's an example of the annual climatology for precipitable water for Chicago. And this, there was a significant flash flood in Chicago in 1996. And if we look at the precipitable water value, go ahead and hit. We'll notice that again, near the 99th percentile, extremely high, 2.10 inches during the peak of the event. So very high precipitable water values for that time of year and just in general. All right, let's go on to the next example. This is Atlanta in 2009, so the annual climatology. And there, notice that in this particular case, it happened later in the year, late September, and the precipitable water value is 2.06 and is above the 99th percentile. So this is a truly extreme event from a precipitable water standpoint. It yielded an extreme event from a flash flood perspective. And this, if you go back, there's actually, in the case of the Atlanta flood, there's actually a nice article in BAMS produced by Marshall Shepard at the University of Georgia. Okay, go ahead, next slide. In the case of the Atlanta flash flood, and in the case of this one, which is in San Antonio from 1998, there's often a tropical component which enhances the moisture profile of the entire atmosphere. So it's, for example, in the case of flash floods, you can have deep moisture at the surface from the Gulf of Mexico, and then a tropical system, like a decaying tropical system such as this, even well removed, can enhance the mid and upper level moisture content, which then yields a very high water content for the entire atmosphere. And so there's often these atmospheric rivers that are connected to these types of events that are bringing mid and upper level moisture in from the tropics. Okay, let's go on to the next slide. And I'm going to talk a little bit more about one last case, and this is the Oklahoma City flash flood. It had ample moisture, some tropical. It had significant instability and a strong low-level jet. A convective outflow boundary stalled south of the Oklahoma City metropolitan area, and convective storms continuously regenerated north of the outflow boundary and moved across Oklahoma City. And the heaviest rain occurred within about 6 hours and included the morning rush hour. So this is the actual sounding from Oklahoma City on June 14, 2010. If you click again, there are a couple of important things. Notice that precipitable water value is really high, 54 millimeters. That's over 2 inches. At the surface, there's the outflow boundary. It had just passed, providing some east winds, and this is, of course, in Norman, so just south of Oklahoma City. So the east winds and the boundary had passed through Norman at this particular point, but just above the surface there is a very strong low-level jet. And these are all important components. There's also, if you can read it, there's also about 2,000 CAPE in this sounding, which represents the significant amount of instability present. But also notice that it's nearly saturated at the surface, and the level of the lifted condensation level and the level of free convection are actually very, very low for this particular event. All right, next slide. So here's the annual climatology of precipitable water for Oklahoma City, Norman area. And if we look at this particular case, there it is, again, above the 99th percentile. So again, an extreme precipitable water event then yields the potential for an extreme precipitation event. All right, let's click on to the next slide. And there's the convective outflow boundary. This is a little bit later in the day, but it's a good representation of, you can see the boundary and then all the convection just north of that boundary. And in the case of Oklahoma City on this particular day, that boundary didn't move a whole lot and allowed storms to continuously train over the Oklahoma City metro over about a 6-hour window. Go ahead, next one. So these are some different locations where we had rain gauges, including the Oklahoma City North Mesonet site, the a gauge in the Central Business District, and then one in between at the Oklahoma City Zoo. And those are values in millimeters there on the left-hand side, so you have to do a little bit of interpretation, but essentially 250 millimeters would be about 10 inches, and you can see that the Oklahoma City North Mesonet site exceeded 10 inches for the event, and while the other sites were actually 6+ inches, 6 to 10 inches, depending on where you're at. Now, most of this fell within about 6 hours, and amazingly, there were no fatalities. There were some dramatic rescues, but no fatalities occurred, which is actually, to this day, is still surprising to me. All right, next slide. Here are the rainfall totals from a number of gauges in and around the area. Amazing rainfall totals in excess of 7 to 8 inches over the Central Business District. North Oklahoma City and extending up towards the Edmond area had over 11 inches and 12-inch rainfall totals. And these represented 500-year flood events, 6-hour 500-year flood events for the area. All right, next slide. And of course, the impacts were significant. Infrastructure failed in the sense of could not remove the water fast enough, and so roadways became flooded, homes became flooded, there were rescues, and I think if you ask the guy there on the right-hand side in that image, I don't think he's too happy about having riverfront property at this point. All right, next slide. So a couple of final thoughts. You know, it's a challenge to, the first challenge is to identify whether a flash flood event or a flash flood risk even exists in the first place, whether it's urban or rural. And then would it impact an urban area? And one of the keys, I think, is just to always look for the extremely high precipitable water values. That will often provide a clue. And then those other ingredients that were mentioned by Maddox et al. And Doswell et al. It's important to also point out that these are happening on convective scales, and so numerical weather prediction models often struggle with identifying locations, very specific locations. If you go back to the Oklahoma City areas, the heaviest rain occurred over a pretty small area, and that is generally the case with most of these types of events. Numerical weather prediction models still struggle with long-term forecasts of such events. And finally, you know, one of the sort of areas of research is, you know, do urban areas actually feed back to impact flash flood events? And at this point, I think there's too little science to make a conclusive, to have a conclusive answer to that question, but it is an ongoing area of research. So with that, I have finished my particular presentation, and I will turn it over to the other presenters.
Thank you so much, Jeff. That was some great information. And unfortunately, having actually been in the Oklahoma City flood on my way to work, that was not a fun experience, but it was definitely amazing to see how quickly the water rose in such a short period of time. So I'd like to turn it now over to Suzanne Van Kooten and her colleagues at the Lower Mississippi River Forecast Center. Due to some technical issues, we don't actually have a PowerPoint presentation from them, but I will be including that in a follow-up email that I send out to everyone, so they'll have the images to view at a later time. So, Suzanne?
And if we could see our presentation, you would be seeing some similar graphics with the precipitable water and soundings and everything like that, so I'll try to walk y'all through it. Basically, what we were going to do was present a case study of a flash flood event that occurred at Karen Crow, Louisiana. That's in southwest Louisiana. It's actually kind of a suburb of Lafayette, Louisiana, Opelousas area over there. So this occurred started coming together on March 11th. We actually had the heaviest rainfall amounts on Monday, March the 12th of 2012, and concluding, and as a low pressure system was moving from the upper air off to the Chicago area on Tuesday, March the 13th. So to set the context, basically rainfall began in southwest Louisiana late Sunday evening. Again, an overnight event. We see that commonly down here with our tropical moisture, rapid influx of surface moisture coming off the Gulf of Mexico. And so our peaks, unfortunately, are at night when people can't see. And then one of the contributing factors here was it continued into the morning hours around daybreak, in through mid-morning, also Monday rush hour, and additionally kids being transported to school. So if there's comments and questions on the social impacts as well as meteorological, we've got our forecasters here from the River Forecast Center, as well as I see online the service hydrologist that we were coordinating very closely with at Lake Charles, Jonathan, Brazil. So what we were looking at as far as going into Sunday morning from a forecasting standpoint, we had a upper low pressure system located in the Texas Panhandle that would take a track from Sunday morning to Monday evening, basically from Amarillo up to Chicago. We had a cold pool aloft that was sitting over basically from Woodward, Oklahoma, to Dalhart, Texas, and a very strong area of height rises coming in southern Arizona, southern New Mexico, and additionally some very strong height falls, minus 10 to minus 12 at 500 millibars, that were setting up basically right along the Texas-Oklahoma Panhandle border there. As far as what we were looking at for the ingredients on Sunday morning, we were having a jet max of about 70 knots that was moving out from the Houston area across Lake Charles, and additionally upper level difluent, basically area where we had a weakness in the flow, where we had the upper level winds at 200 millibars peeling off to the north across basically Texarkana to Little Rock, and then going almost due west from Lake Charles over across the New Orleans, Mobile area. And so that sets the context for Sunday morning. At the surface, we were seeing very strong advection of Gulf moisture and much higher dew points coming in. The Theta E ridge and the surface, the main surface thermal axis was basically running from about Key West across the Gulf of Mexico up into Houston. We had a cold front working basically from Dallas-Fort Worth, Texas, down to Brownsville, and of course a warm front that was extending from Dallas-Fort Worth across Shreveport to about Jackson, Mississippi. So the area that we were looking at in Karen Crow, Louisiana, Lafayette area, we basically had a jet 70 knots at 200 millibars coming across the top of it for Sunday morning, and additionally a strong area of warm air advection with higher and Theta E ridge basically extending into Lake Charles. So that was the Sunday morning kind of setup with that. What we saw Sunday morning, 12Z, was we had the low pressure center rotating, but a large area of precipitation with some embedded thunderstorms extending across most of Oklahoma, the Houston area, most of Arkansas, and that area was continuing to work its way to the east. So from our soundings, basically if you would look at the Shreveport, Lake Charles, Jackson, and Slidell soundings on that Sunday morning, Shreveport was saturated up to about 500 millibars. Again, they had the areas of showers and thunderstorms moving into the area, and we had some instability and in Lake Charles, Jackson, and Slidell, and I'll take that through kind of a synopsis of where we were changing with that. Again, this is Sunday morning. By Sunday night, when we were going into the evening hours, that upper level low pressure at 500 millibars was sitting over basically Wichita, Kansas, with a surface trough extending from that down through central Oklahoma, and a pretty strong 500 millibar cold pool working its way through Texas. The upper level jet of 70 knots was basically a line from Texarkana up to Springfield, and the 200 millibar difluence area had actually moved up to the north. We were in very weak upper level forcing mechanisms across Lake Charles area, New Orleans, southern Louisiana, pretty weak with the forcing in the upper levels. At the surface by then, going into the evening, we had seen that theta E ridge at the surface in mid-level start to work its way basically from Lake Charles, the nose of it working up towards the Memphis area, and the surface instability was starting to come together. We had, going into the early evening hours, a squall line that was basically stretching from eastern Arkansas down through most of northern Louisiana, and then additionally extending down through Lake Charles and into the western Gulf of Mexico. Again, we had some very strong convection embedded in this area. The main stratiform rain shield was extending all the way up into Nebraska and central Iowa. So in the evening hours, what we had going in, we were seeing basically our instabilities really coming up off of the Lake Charles sounding. To give you an example, the Showalter Index from the Sunday morning sounding was 1.61. By the evening hours on the 00Z, we were at minus 4.67. Additionally, the precipitable waters at Lake Charles really came up. From the 12Z in the morning, we had a 1.44 inches of precipitable water on that sounding. By the evening sounding on Sunday, prior to the heavy rainfall event really turning on, we had increased that precipitable water up to about 2.04 inches. And that is actually a maximum off of that site that Jeff showed on his earlier slides. That's actually a maximum for Lake Charles for the month of March, is 2.04. So we were starting to set the stage, seeing things coming together as far as the moisture content that evening. But again, the upper level forcing mechanisms were a little different. So as we go in to the Monday morning time frame, what we saw then was the upper level low was starting to fill in and weaken. It was now located up north of Kansas City, Missouri. We didn't really have a jet max coming across. There was one about 60 to 70 knots at 200 millibars, but it was basically located from El Paso going up towards Shreveport. So we were in pretty weak flow aloft. The height rises and falls, again, with the filling of the 500 millibar low, weren't that dramatic. So the 12Z surface analysis that we were looking at for Monday morning in the radar loop, you'll see, we were really having some very heavy rainfall, very, very efficient storms forming around Lake Charles, and hardly any surface winds at all with this. And again, just sitting offshore of Lake Charles, we were having 72-degree dew points. So we could still detect, although it was faint, the theta E ridge and that moisture advection coming into those storms. So basically, by Monday morning, what we saw was we had the main area of convection and embedded thunderstorms had moved over across the New Orleans area, was extending over to Mobile up to the Jackson area. But we had some residual cells that were beginning to form and refire over the Lake Charles area, extending over to the Lafayette metropolitan area and up towards Alexandria. So we started seeing this redevelopment back behind the first wave of storms on a Monday morning, right around daybreak. So with that, let's go ahead and skip through because you're going to post the slides online. What we were seeing was, and when we came in here at the Lower Mississippi River Forecast Center, We have an on-call number, and additionally, we staff routinely beginning at 6 a.m. When we came in on the radar scope, what we were looking at was over the Vermilion Basin, Lake Charles area, some very heavy convection embedded in a larger area of rainfall. And then as we continued to watch the radar loops, we continued to do what Jeff was saying, training, but additionally also back building. We had a lot of very fine boundaries that were being laid down, outflow boundaries as each one of these thunderstorm clusters went up, and then it just kept back building and just kept reforming, basically over the same area of the Lafayette metropolitan area, unfortunately. Again, Monday morning, daybreak, rush hour, kids trying to get to school. So from the National Severe Storm Lab, in their Hydrometeorological Research Division, there's a product in it, the product suite that's been developed called NMQ. And in that product suite, they have vertical profiles of reflectivity. And basically, we use that as a tool at Lower Mississippi River Forecast Center to look at basically, are we having a continental air mass where we have a very defined bright band layer along the freezing level of the atmosphere with storms, or are we in a warm rain event, a tropical air mass event where we have very high precipitation efficiency? And in those types, you don't see any nodes of higher reflectivity along the freezing level. So when we were looking at this in real time and diagnosing if there was a warm rain process, basically we were looking at the vertical profiles of reflectivity from National Severe Storms Lab, and we were seeing a tropical air mass and this process going on. So as we were also pulling in the gauge data, we were looking at one of our gauges, BVCL1 at Karen Crow. And so basically what we were seeing from our rainfall rates was from 12 to 13 UTC, we got 1.23 inches of rain. The next hour, the 13 to 14 UTC on Monday morning, which would have been 7 to about 8 to 9 a.m. Monday morning, we had a 1 hour rainfall rate of 3.54 recorded at that gauge. From the next hour, the 14 to 15 UTC, we had 5.13 inches of rain recorded in 1 hour. And 15 to 16 UTC, we had 1.56 inches of rain. Basically, for this event, what we had about a little over 15 inches of rain at the BVCL1 gauge, the Karen Crow gauge, that's co-located with our stream gauging network there. In this rainfall event, and I'll sum that up. Y'all have in there, you'll be looking at a slide that shows the gauge-adjusted radar and the 24-hour QPE accumulation. The area of the heaviest rainfall was actually north of our gauging network. We did not have any gauges right where this actually fell. And so with that, our rainfall rates and precipitation rates coming from the radar estimates from NSSL, we were estimating greater than 10 inches. But our thresholding is 10 inches or greater, so that's why we were using the hourly rainfall rates that we were getting in. To give you an example for the social impacts of this, where the heaviest rainfall actually occurred was, thank goodness, north of the Lafayette metropolitan area. And we have the terrain map also that you'll be able to see in the presentation. What this, and thank goodness it happened up there, rather than falling in the impervious area of the urban area of Lafayette, was basically, we could have had just straight sheet flow is what we call it. We would have had no place for this to even run off into. We would have had limited soil profiles and everything. So thank goodness this actually occurred 10 miles north of the greater Lafayette area. What we saw at Bayou Vermilion near Karen Crow, the BVCL1 gauge, was basically from 6 a.m. on Monday morning. We started out with a river stage of 8.41 feet. time we got to 9 a.m., so 4 hours later, we were at 14.56 feet. We'd already climbed almost 6.5 feet on a river stage. And by the time we were going into about 4 o'clock in the afternoon, we were at 22.49 feet on that gauge. Again, 6 a.m. in the morning at Bayou Vermilion, we were at an 8.41 foot river stage. And by 4 in the afternoon, we were at 22.49. So basically 14 feet in basically about a foot an hour, 2 feet an hour. So very dramatic on the increase of the river stage over there. But again, you have to remember, we had 1 hour rainfall rates in there at that time of 5.13 inches of rain. We had similar results in the city of Lafayette at urban gauges, where we basically started at about 4 feet in the morning hours, and we were up into about 8 feet by the afternoon. We basically there were climbing about, at the beginning of the flash flood had been about a foot an hour, and then as we tailed into it, about a half a foot rise as we went on into the later afternoon hours. So from a thresholding standpoint of the historical context, we had rainfall intensities over 1, 3, 6, 12, and 24-hour durations that broke our 1% chance event climatology. We crested at Bayou Vermilion at Cairn Crow at about 22.5 feet. That was about 1 foot above the previous record for that gauge. And the floodwaters in the Vermilion Basin, very slow to recede. Not much relief down here, not much terrain, and so basically it comes in and it fills up and it sits. And so preliminaries were over 500 homes reported as flooded. That was increased. To close basically with our forecasting methodology, and again we have links for you to see just the extent and YouTube videos. A lot of it was posted, and everybody here, Jessica Smith, our senior, has, Scott Lincoln, our hydrologist, and Jonathan Brazil have absolutely been fabulous in trying to archive not only the meteorology but also the human impacts, and just for the extent of this, that we'll have that for everybody who's on here. The forecasting methodology, to close with, we were nearing a minor crest, and we were trying to work up the highest crest that we could get, realizing that this exceeds a 1% chance. We realized we were already exceeding the 1% event for the 12-hour duration, and we were almost there for a 24-hour duration. We were using some new tools that, honestly, we adapted. We were like, let's see how this works. Our 1% event, we were estimating would come in around 23 feet. And then Jessica and Scott with Jonathan worked up the estimate for a 22 to a 23-foot crest estimate from that relation. We were basically going from the rarity of the precipitation event to the rarity of the hydrology event. And that was pretty darn close, because we actually crested in around the 22.5 mark right about 5 p.m. on Monday afternoon. We maintained the 22 to 23 foot crest when we were coordinating with the WFO of Lake Charles. And this is an interesting thing for social impacts and how to convey messaging and how to get people to do the right things with the information. While we were working this crest up on conference calls between Lake Charles and the Lower Mississippi River Forecast Center, we were getting storm reports of water rescues and rescue of children from stranded buses. This is the morning when you're trying to get them to school. And so because of that, we knew we had another tool with us to communicate just the severity of the event. So we mentioned to the Lake Charles service hydrologist that this was a very rare event and the severity of the flood, and we might just need to up this. And so we did go out and use, and Lake Charles, to their credit, went out and used our rare wording of a flash flood emergency. It's similar to the WFOs when they go out and we issue tornado emergencies now. And so we did use that, and it did pan out very well with people to convey the implications and also just the severity of the situation. So again, I apologize that we do not have the slideshow up, but again, we can answer questions, and please feel free to email directly through Margaret, and we'll get you the information you need. So I'll close with that.
Thank you, Suzette. That's very interesting information, and as Jeff mentioned earlier, it just goes to show that flash flooding is not limited to one particular region. It can occur anywhere. I'd now like to turn it over to Andy Wood with the Warning Decision Training Branch, who will talk a little bit about the new dual polarization radar upgrades. Andy?
Hi, everybody out there. I'm Andy Wood. I am an employee of the Cooperative Institute of Mesoscale Meteorological Studies, and I am located at the National Weather Service Warning Decision Training Branch. I've been involved quite a bit with the operations training on the dual pole radar for the Weather Service, as well as the outreach training that we've made available for people outside the Weather Service. So I'm going to talk a little bit about how the upgraded 88D for dual pole will impact flash flood forecasting. Next slide, please. Trying to get into all the details about the dual pole upgrade is going to be a little difficult in this context, but at the end of the presentation I'll have some URLs that if you want more background information on the dual pole upgrade, if you're not familiar with some of the basic details, you can look at those. But the 88D upgrade is the most significant update to the radar since its original deployment back in the 1990s. And really what I'm going to focus here on is two different things. There's the legacy precipitation products that have been available for the last 2 decades, and the new dual pole precipitation products that are now available because of the upgrade, and just comparing and contrasting those two. Also, looking a little bit at the dual pole base data and being able to do some qualitative analysis versus the quantitative analysis that you might do using the precipitation products. So real quick, here is a map that's showing the current progress of the dual pole upgrade. The red dots on the map show all of the locations that have been upgraded, and the blue dots are the areas that haven't been upgraded just yet. So you still have a large area there along the Gulf Coast that haven't been upgraded to dual pole quite yet, as well as a few other spots in the central part of the United States and other places like Hawaii and Alaska. But things are progressing, and in about another 6 months or so, everything should be upgraded to dual pole. Now, when we're talking about the dual pole precipitation products that will be available, one of the things that's really important to remember is that the legacy precipitation products that you're used to using aren't going anywhere anytime soon. They are still available. You can still use them from whatever provider that you currently use. The dual pole products that are available are in addition to that. There will be essentially dual pole versions of those legacy precipitation products that are available. So you'll have multiple products that you can look at, say, for 1 hour precipitation. So you can almost do a little bit of ensemble there between the two products and compare them and see what's going on. But in addition to those duplicates, you will also have a few new products. And two examples of that are the instantaneous rate as well as the hydrometeor classification products. So if I go into a little bit more detail in terms of kind of the tail of the tape between the two suites of products, with the legacy precipitation products, they would rely on the reflectivity products to generate a digital hybrid reflectivity, which would then be used to calculate your rain rate. Now, because this is a more mature algorithm, there's been different changes that have been made over the years. They've made it now where the rain rate that you use through your reflectivity is configurable. So depending on whether you had a more tropical air mass or more of a continental air mass, you could adjust the equation that you used. You also had the ability to incorporate gauge data and apply bias to those estimates as well if the office chose to do so. So there was lots of things that they could do to adjust the product and make the radar data or the rainfall data as quality as possible. Now if we advance to the next bullet there, for the new dual pole algorithm, this algorithm is still a bit in its infancy. It's new, and it incorporates a lot more data. In addition to just the reflectivity data, it incorporates some new dual pole base data differential reflectivity, correlation coefficient, and specific differential phase. It also takes into account the melting layer, which is either determined from the radar data itself or using RAP model data. And then it uses all that to create a hybrid hydrometeor classification. And from that, it will generate your rainfall estimates. But instead of just using a simple R sub Z relationship, it may use R sub Z. It could use an equation using both reflectivity and differential reflectivity, or just using specific differential phase. So it all depends on the type of hydrometeor classification the algorithm comes up with. But because, I'll click one back one sec there. Because the algorithm's still in its infancy, the rain rate equations are more or less set. They're not configurable yet. Hopefully in the next several years, more research can be done to change those, as well as add the bias correction into the equations. So here's a suite of the new dual pole products that are available. The first 8 on this list are level 3 products that you may be able to access through your NIDS feed depending on how you access your radar data. The one thing I will say, if we click on the next animation here, you probably want to stay away from the difference products. One of the nuances between the 2 precipitation product suites is that the resolution of the products are different. So the difference products will essentially be comparing, because of that, you get some interesting artifacts in the output data. So sometimes you'll see features in the difference products that are simply a difference of resolution of the input products. And so it can be a little confusing to interpret. In time, hopefully the legacy and dual pole QPE products will have the same resolution, so these difference fields will be a lot more useful. But it's just what we've noticed in the last year and a half is that they're a little confusing to use, at least at this point. Go to the next slide. Here's just a few examples of the dual pole products. We have a dual pole 1-hour accumulation, which is just like the current 1-hour precipitation product from the legacy rainfall estimates in the radar. The one I have up here is actually, it's a 4-bit product, but you actually can get 8-bit 1-hour accumulation with dual pole, which is what gets into that difference field discrepancy I was just talking about. But 2 examples, the hybrid hydrometeor classification. This product is what the algorithm actually uses to generate the precipitation estimate products based on what field is come up with those different colors there. And then what comes out of that is actually going to be your digital precipitation rate, which is on the right side, which is actually a 16-bit product, so it has quite a bit of resolution. But it would take each of those digital precipitation rate products and then from that come up with, say, your hourly accumulation or your snow total accumulation. Slide, please. And as Susan was talking about earlier, the NMQ site is probably one of the better sites that I at least know of in terms of for people who want to look at some of this additional dual pole radar rainfall information. It's not necessarily for looking at this product versus that product, but especially for these larger mosaics and you want to try to get the highest quality rainfall estimates possible. It's a good site, and the folks there are actually looking at the dual pole products individually and comparing them to the legacy products to find ways to improve the data quality of the rainfall estimates. So they've been quite helpful. Slide, please. Now, just quickly, the strengths of the dual pole quantitative analysis. It really works well during the warm season, especially in areas below the melting layer. It really can help, especially in areas where you might have hail mitigation, or you need hail mitigation, I should say. So if you have a lot of hail contamination and you're trying to take that out of your rainfall estimates, dual pole does very well with that. It also does well with removing any non-meteorological echoes so that they are not counted towards your rainfall totals. And it can also help quite a bit if you have a significant bright band. It can help reduce the rainfall totals in those areas. If we look at the next slide, it'll have the limitations. As we said, dual pole works fairly well during the warm season. There are definitely some limitations during the cool season. The National Severe Storms Lab is working on updating that. The research that went into creating the algorithm was done primarily with warm season cases. So that's just one of the byproducts of that. And because of that, they usually it was only areas far from the radar that were above the melting layer, and so they had to apply a multiplier to the rain rate equation in those areas. And so during cool seasons, you can see significant overestimates of rainfall in areas above the melting layer. Another issue that you can have with the dual pole quantitative estimates is that if you do have any data quality issues in your base data, there's so much data that goes into the algorithm that little data quality issues in the base data can result in big issues with data quality in the precipitation estimates. And it can be in the base data. You can also have issues with melting layer. We've had some issues where the melting layer product has had a significant deviance of what the actual melting layer is, and that has caused problems, as well as issues with hydrometeor classification. So if I go to the next slide here, I've been talking about more of a quantitative analysis of rainfall. One of the things that's nice about the dual polarization technology is it allows you to do some qualitative analysis as well. Instead of using the RPG or radar product generator algorithm output for accumulations or rainfall rate, you can actually look at the base data and look at fields of rain and try to determine where the heavy rain is in there. This can be especially useful going back to what Jeff was talking about. If you have areas where it's very localized heavy rain and maybe the reflectivity values are fairly similar, it can be difficult to see where the heavy rain is actually occurring. But the dual polarization base data can actually help with that quite a bit. Next slide, please. So here's a quick example using reflectivity and one of the dual pole products called specific differential phase. And so in this case, we've got a storm near the Tucson area with you click on the next animation, you can see in the white outline, you've got a fairly decent area of 55 dBZs in both products. But if we do the next animation, there, in that black outline area is where in the specific differential phase, which is a nice proxy for liquid water content in the precipitation, you can see you have a large amount of liquid water content towards the northeastern part of that core and not as much to the southwest. So if we click on the next animation, what this means is in the northern part of that core where the reflectivities are maybe a little bit less, that is the area where you have the heaviest rain. Whereas the area where the reflectivities are a touch more, that's where you have some hail contamination and your actual liquid water content there is not quite as much. So using specific differential phase here, but you can also use the other dual pole base data, it can help forecasters quite a bit build their confidence in these particular areas where heavy rain may be occurring. So if we go to the next slide, just the strengths of doing this kind of qualitative analysis is that it does increase the forecaster's confidence in radar signatures of heavy rain. And where this really comes through is in cases where you might have a tropical warm rain event, or if you're worried about whether maybe it is more of a continental rain, especially some places you may have both of those things going on at the same time and you're trying to differentiate between the two. It's also very helpful if you do have areas where you have hail and rain differentiating between the two, like in the example I just shown. But it also can be very helpful with cases where you have hail that is melting, and you can get some nice signatures in the dual pole data of the melting hail as well. Slide, please. Now, the limitations of doing this type of analysis is that, say, with the specific differential phase or KDP, the values don't always translate into your actual QPE products. The actual equations that are used for rain rate, they will only use specific differential phase if you have an area where there is hail or if you have some beam blockage. So sometimes there may not be a true one-to-one relationship in what you're seeing in your quantitative products versus your qualitative products. Next animation. The other issue you have is even though the specific differential phase values are computed, sometimes they do drop out, especially when the correlation coefficient values are below 0.9. When correlation coefficient gets that low, it's a sign that your data quality may not be as good in the dual pole products. And so specific differential phase can be a bit noisy, and so if the data quality seems to be degraded, those data are not computed or shown, or they're computed, but they're not shown in the products. Next slide, please. So just briefly in summary, The dual pole upgrade is the most significant upgrade to the 88D since it was originally installed. Adding dual pole technology allows us to do not just a quantitative analysis with this new data, but also a qualitative analysis. The quantitative analysis with dual pole is going to be best during the warm season, especially for echoes that are going to be detected by the radar below the melting layer. And where it's currently shown the most promise is with convective events that have potential hail contamination. However, with the qualitative analysis, it can help when you're looking at the quantitative products in terms of trying to identify areas where you think there are heavy rain. It can help increase your confidence in those signatures of heavy rain. On the last slide, I have my contact info, as well as the websites for the training that we have available with the Warning Decision Training Branch, as well as the Radar Operations Center's website, where they have a lot of information about dual polarization upgrade schedules and other technical information. I know especially for those of you who might be along the Gulf Coast, you can monitor the progress of when your radar will be upgraded there. If anybody has any questions, I'll be glad to answer them.
Thank you, Andy. I think that's some great information for everybody, especially since dual pole is almost completely installed across the United States now. I just want to say a quick thanks to all of our presenters, Jeff, Suzanne, and our colleagues, and Andy, for providing some great information today. We'll now open it up to any more questions or comments that you'd like to post in the chat box if you have any. And then we'll leave this list of resources up on the screen if there's anything you'd like to look into further. All the presentation materials from today's webinar will be posted to our SCIP website. We'll also make a 2-page PDF summary. We'll post that, and then we'll also email it out to everybody. And then the webinar is also being recorded today, and we'll post that to our SCIP YouTube if you'd like to go back and rewatch it, or send it on to your colleagues. And we'll also link that to our various social media sites as well. So we encourage you to continue to prepare and spread the word to make sure all of those dealing with planning, preparation, and mitigation efforts of extreme events and hazards are involved with this new series. You can pass along any of the information that we provide, the PDF summaries, the webinar announcements, or any of the other information. And we may have a few more comments coming in. We'll leave the chat box open for just a minute. But if not, we would like to just thank you for your time, and we look forward to continuing this conversation in the future. And as it looks like one of the links that was actually on the resource page, as the Lower Mississippi River Forecast Center provided, need to drop out everything after the second slash. That was a error in copy and paste. But then that should work if you'd like to access their website as well. So if there's not any more comments, I'll just again say thank you, and we'll be sending out the information to you shortly.